Far beyond our skies lies the Whirlpool Galaxy, a perfect spiral caught in a cosmic dance of collision with its smaller companion. This encounter is rewriting the stars and shaping worlds we may never see. Why do galaxies collide, and what does it mean for the universe? If you enjoy this journey, please like, subscribe and share, and tell us in the comments, what would you ask if you could witness such a galactic collision up close? Thank you for watching. Now, let's begin. The Whirlpool Galaxy is first noticed as a distinct spiral shape when telescopes begin to show enough detail to trace its form. In the middle of the 19th century, William Parsons, the 3rd Earl of Ross, sketches what he sees through the large telescope at Birr Castle in Ireland. His drawing shows curved arms winding out from a central region, and this makes the Whirlpool Galaxy one of the earliest objects to be recognised as a spiral nebula. Before this, faint patches of light are often described without clarity about their structure, and many are assumed to be nearby clouds within the Milky Way. The Whirlpool Galaxy stands out because the spiral pattern is drawn with a precision that suggests an ordered and coherent structure, not simply a formless haze. The object is catalogued as Messier 51 with the designation NGC 5194, assigned later in the New General Catalogue. At first, the naming systems are purely for reference, but over time the numbers are linked with deeper understanding of distance, mass and structure. When astronomers look at the whirlpool in small instruments, they see a soft glow with a brighter centre. In larger telescopes, the spiral arms appear more sharply, and the smaller companion galaxy NGC 5195 becomes clear positioned just off the main disk. Even in direct observation, the system presents an example of interaction with the smaller galaxy, seeming to connect by a faint bridge of light. Photography allows a more permanent record than sketches. In the late 19th century, long exposure images are made that show detail beyond what the human eye can hold at once. These photographs reveal the continuity of the spiral arms, the dark lanes of dust and the knots of light along the structure. The whirlpool becomes one of the most studied galaxies in the sky, serving as a test case for theories of spiral structure. It is also visible to amateur astronomers in small telescopes, so the same object is observed across a wide range of expertise and equipment. The position of the Whirlpool Galaxy is in the constellation Canes Venatici, near the tip of the handle of the Big Dipper. From Earth, it lies just north of the celestial equator, making it visible from most inhabited latitudes. The apparent brightness is enough for a small telescope to reveal its form under dark skies, though to the naked eye it is not detectable. Observers in the Northern Hemisphere have long used its location near familiar constellations as a reference point in learning the deep sky. The angle of view from Earth places the disk nearly face-on, which is unusual compared to the more common oblique views of spiral galaxies. This orientation makes the whirlpool especially valuable in the study of spiral arms since the pattern is laid out broadly rather than tilted. Early questions about the whirlpool concern its distance. For a long time it is not known whether spiral nebulae are objects within the Milky Way, or separate galaxies altogether. The famous debate between Harlow Shapley and Heber Curtis in the early 20th century centres on this issue with the whirlpool as one of the examples under consideration, when Edwin Hubble identifies Cepheid variable stars in the Andromeda Galaxy. Proving that it lies far beyond the Milky Way, the same logic is extended to the whirlpool. Over time, distance estimates refine, placing it about 23 million light-years away. This shows that its size is comparable to the Milky Way with a disk tens of thousands of light-years across. With distance established, the whirlpool can be studied as a galaxy in its own right. Astronomers consider its mass composition and dynamics. Spectroscopy reveals the types of stars present, the composition of gas, and the motion of material along the line of sight. The bright knots of emission show regions where gas is ionized by young stars, indicating recent star formation. Dust lanes trace out regions where light is absorbed, showing where gas is dense enough to block starlight. The face-on view allows a direct comparison of arms on opposite sides, which are found to be broadly symmetric, but with local differences in brightness and structure. The small companion NGC 5195 is first described as a faint blob near the main galaxy, but its significance grows as the study of galactic interactions advances. The apparent bridge of light connecting it to the whirlpool suggests that tidal forces are at play. Models of interacting galaxies later confirm that close passes can draw out material trigger waves in the disk and stimulate star formation. In the case of the whirlpool, the symmetry of its arms may be enhanced by the influence of the smaller companion, which provides an external force to organize the pattern. As telescopes increase in size and sensitivity, details of the whirlpool are measured across many bands of light. Neutral hydrogen is mapped with radio receivers, showing that the gaseous disk extends far beyond the visible starlight. This neutral gas is the main reservoir for forming future stars, and its motion provides information on the overall gravitational potential. In the optical band emission lines from hydrogen mark the places where massive stars have recently formed and are heating their surroundings. The dust lanes are studied more deeply with infrared detectors, which reveal cooler structures invisible to visible light. These images show how dust both obscures and traces the densest regions of gas. Observations in the ultraviolet emphasize the youngest and hottest stars, which highlight the continuous pattern of the arms more clearly. At higher energies, X-ray images reveal sources such as remnants of exploded stars and compact objects that are accreting matter. By piecing together all of these bands, astronomers begin to build a multi-layered description of the whirlpool. Each wavelength adds detail about different components, from cold gas to hot plasma, from young stars to ancient populations. This approach transforms the whirlpool from a simple spiral in a sketchbook to a complex system observed through many windows of the spectrum. The companion galaxy NGC 5195 is introduced as a smaller, irregular system located near the Whirlpool Galaxy. It is not simply an object in the same line of sight, but is physically close enough to exert gravitational influence. In images, it appears just off the edge of the larger spiral disk, connected by a faint stream of stars and gas. This bridge is interpreted as evidence of a past close encounter in which material was drawn out by tidal forces. Careful observations in both optical light and radio frequencies confirm that the two galaxies are interacting with measurable distortions in their shapes and motions. The smaller companion is estimated to have only a fraction of the mass of the whirlpool, yet its gravitational presence is sufficient to disturb the much larger disk. The stellar populations of the companion are studied to understand its nature. Unlike the well-defined spiral arms of the Whirlpool NGC 5195 shows a looser and more irregular structure. Its stars are distributed in a clumpy pattern, and it lacks the symmetry of a grand spiral. Observations of its spectrum reveal a mix of older stars and regions of active star formation, suggesting that the interaction with the whirlpool has stimulated bursts of new stellar birth. The companion is thought to contain large amounts of gas, which can be compressed during tidal interactions to ignite new clusters of stars. The brightness of the bridge between the galaxies indicates the presence of both stars and gas. Stars can be drawn out by gravitational tides, but gas responds more strongly because it is less tightly bound. Along the bridge, emission lines from hydrogen are observed, showing that ionized regions have formed there as well. These are interpreted as sites where gas clouds have collapsed and new stars are forming even in the connecting stream. This demonstrates how galaxy interactions do not only disrupt, but also trigger creative processes of star formation. The whirlpool and its companion together provide a clear example of how close passes redistribute material and reshape galaxies over time. Careful mapping of velocity fields helps astronomers determine the dynamics of the system. Using spectroscopy, shifts in the wavelengths of spectral lines reveal whether gas and stars are moving toward or away from Earth. These measurements show that the companion is not simply orbiting in a circular path, but is in a complex trajectory influenced by both its own momentum and the gravitational pull of the whirlpool. Models suggest that the smaller galaxy may have passed through or very near the disk of the whirlpool in the past few 100 million years. Such an encounter would explain the symmetric pattern of the whirlpool's spiral arms, which can be maintained by the forcing of an external companion. Radio observations of neutral hydrogen extend the picture. Large-scale maps reveal streams of gas that extend beyond the visible images linking the two galaxies in a wider envelope. These structures are faint in optical light but clear in radio frequency surveys. The amount of gas displaced is significant, showing that even a smaller galaxy can draw out large masses of material when passing close to a larger disk. The companion itself shows asymmetries in its own gas distribution, confirming that it is also being affected by the interaction. The two systems are locked in a gravitational exchange, shaping each other's evolution. Infrared studies with instruments such as the Spitzer Space Telescope show regions of dust warmed by starlight in both galaxies. In the companion, the dust glow is concentrated in patches corresponding to active star-forming regions. The bridge also shows faint emission, supporting the idea that dust and gas stripped from the galaxies are being heated by young stars forming in situ. Infrared data provide estimates of the rate of star formation by measuring the total luminosity of dust emission. These measurements confirm that the interaction enhances the overall rate of stellar birth compared to isolated galaxies of similar type. X-ray observations add another layer. The region between the galaxies hosts sources of high-energy radiation, including compact remnants such as neutron stars and black holes accreting matter. Some of these are likely formed from massive stars born in the recent bursts of star formation triggered by the interaction. The presence of X-ray binaries indicates a young stellar population that has already produced remnants. The distribution of these sources is not uniform but traces the same structures visible in optical and radio bands, further tying together the multi-wavelength picture. The relative sizes of the two galaxies highlight the scale of the interaction. The Whirlpool Galaxy spans tens of thousands of light-years and contains hundreds of billions of stars. The companion is much smaller, containing only a few billion stars and a much lower mass. Yet the laws of gravity make even this smaller body capable of exerting strong tidal forces when passing close enough. Over cosmological timescales, such interactions are common, and they play a major role in shaping galaxies. In this case, the companion does not merge immediately with the whirlpool but orbits around it in a bound path. Each passage perturbs the spiral structure further, and eventually a full merger may occur, but only after many cycles of interaction. The appearance of the whirlpool and its companion provides astronomers with a natural laboratory. The nearly face-on orientation allows clear visualization of the arms, the bridge, and the distortions. Unlike more distant systems, the relative closeness of this pair at about 23 million light-years makes detailed study possible, with a wide range of instruments. Observers can examine everything from the faint outer gas envelopes to the compact high-energy sources near the nuclei. This combination of clarity and complexity makes the Whirlpool system one of the best examples for studying galactic interactions. The companion's role continues to be tested in simulations. Computer models attempt to reproduce the observed features by adjusting orbital paths, mass ratios, and timing of encounters. The symmetry of the Whirlpool's arms, the brightness of its bridge, and the distortion of the companion are all constraints on these models. Simulations suggest that the companion has already passed through the disk once, and is now on a path that will bring it back again in the future. These repeated encounters can sustain the spiral pattern for long durations, while also fueling bursts of star formation. The interaction is therefore not a single event but part of a longer sequence of gravitational exchanges. The Whirlpool Galaxy is classified as a grand design spiral, a term used to describe galaxies whose spiral arms are well defined and continuous across the disk. This is in contrast to flocculent spirals, where the arms appear broken or patchy. In the case of Messier 51, the arms can be traced smoothly for large fractions of a circle around the central bulge. They do not fragment into small pieces but maintain coherence across many tens of thousands of light years. This makes the Whirlpool an ideal system for studying the nature of spiral structure. Its nearly face-on orientation enhances this clarity, allowing astronomers to measure the pitch angle of the arms, their spacing and their continuity without the complications of strong projection effects. The spiral arms are not made of a fixed set of stars arranged like beads on a string. Instead, they represent regions of higher density through which stars and gas pass as they orbit the center. This concept, called density wave theory, explains why the arms persist for billions of years rather than winding up tightly as the galaxy rotates. According to this view, the arms are patterns moving through the disk, similar to a traffic jam on a highway, where cars move in and out but the overall congestion remains. In the Whirlpool observations confirm that the stars in the arms are not the same at all times, but the structure of the arms is maintained across long time scales. Measurements of the pattern speed of the spiral give insight into how the arms evolve. Pattern speed refers to the angular velocity at which the density wave rotates around the galaxy. Stars closer to the center move faster than those in the outer disk, but the pattern itself rotates at a relatively constant rate. This difference is what allows the arms to be long-lasting patterns rather than material features. In the Whirlpool studies of star-forming regions, clusters and gas clouds provide evidence for a stable pattern speed. The arms are also symmetric, with two main arms dominating the structure, which is characteristic of grand design spirals. The presence of a close companion adds complexity to this picture. While density wave theory explains spiral arms in isolation, tidal interactions can also induce or reinforce spiral patterns. In the case of the Whirlpool, the smaller galaxy, NGC 5195, provides an external force that may strengthen the arms and help maintain their symmetry. Simulations of the interaction show that a close passage of the companion can drive waves into the disk of the Whirlpool, which then appear as spiral arms. These tidal arms can be nearly as regular as density wave arms, and in practice the two processes may operate together. Observations suggest that the Whirlpool's structure is not solely due to internal dynamics, but is shaped by the ongoing gravitational exchange with its neighbor. Dust lanes provide a visible tracer of the spiral pattern. In optical images, the arms of the Whirlpool are lined with dark filaments where interstellar dust absorbs starlight. These lanes lie on the inner edges of the arms relative to the direction of rotation, consistent with the predictions of density wave theory. As gas enters a density wave, it is compressed, triggering the formation of molecular clouds. These dense clouds are laced with dust, and the dust blocks light from behind, creating the prominent dark streaks. By mapping these lanes, astronomers can identify the shocks where gas is being compressed, and star formation is likely to follow. Star-forming regions are distributed along the arms in bright knots. These regions contain ionized hydrogen gas known as H2 regions, which glow in characteristic emission lines. They mark the places where massive young stars are energizing their surroundings with ultraviolet radiation. In the Whirlpool, the H2 regions are especially prominent, forming a chain of glowing patches that outline the spiral pattern. This is further evidence that the arms are density waves, since the gas compressed by the waveform stars that quickly light up the surrounding material. These bright regions are short-lived on cosmic timescales, since massive stars burn out in only a few million years, but they continue to appear as the arms rotate through fresh gas. The continuity of the arms allows detailed measurement of pitch angle, the angle between the tangent to the spiral and a circle around the center. The Whirlpool's arms have a moderate pitch angle, neither tightly wound nor extremely open. This angle is related to the mass distribution of the galaxy and the speed of rotation. By comparing observed pitch angles with theoretical predictions, astronomers test models of spiral structure. In Messier 51, the measured pitch angle supports the idea that its arms are shaped both by internal density waves and by external tidal forcing. The arms also show a high degree of symmetry, suggesting that the companion's influence is balanced on both sides of the disk. The study of spiral arms in the Whirlpool has broader implications. Spiral structure is one of the most common features in disk galaxies, but the mechanisms that sustain it are not fully understood. By examining a clear example like Messier 51, astronomers can refine theories that apply to other galaxies, including the Milky Way. The Milky Way's spiral arms are harder to study from within, since our view is blocked by dust and limited by our position inside the disk. In contrast, the Whirlpool presents a clean external view of a system with well-defined arms. Measurements of star formation rates, gas distributions, and magnetic fields in its arms provide a template against which other galaxies can be compared. Observations across different wavelengths continue to highlight different aspects of the spiral structure. In ultraviolet light, the arms appear as bright ribbons of young stars. In infrared, the arms are traced by the glow of warm dust, showing where dense molecular clouds are located. In radio frequencies, the arms are mapped by emission from carbon monoxide, a tracer of cold molecular gas. Each wavelength reveals a different phase of the interstellar medium, but all align along the same spiral pattern. This confirms that the arms are regions of overall compression, where gas, dust, and stars are concentrated together. The Whirlpool Galaxy therefore provides an especially clear case of a grand design spiral with arms that are continuous, symmetric, and active in forming stars. Its structure is not static, but maintained by the combination of density waves and tidal interactions. The nearly face-on orientation allows all these features to be observed in detail, making it a cornerstone object for understanding spiral galaxies. The idea of density waves provides a framework for explaining the spiral structure of the Whirlpool Galaxy. In this picture, the arms are not static streams of stars, but rather patterns of higher density that move through the disk. Stars and gas enter the pattern and leave it again, much like vehicles passing through a slow zone on a road. The density wave maintains its form while individual stars and clouds move in and out of it. This resolves the problem known as the winding dilemma, where simple orbital motion would otherwise wrap the arms too tightly over time. For the Whirlpool, the persistence of its two main symmetric arms supports the idea that a density wave pattern is present. The mathematical description of density waves comes from the application of fluid dynamics and gravitational theory to galactic disks. The disk of a galaxy is treated as a rotating system with many stars and clouds moving under gravity. Perturbations in density can grow into stable wave patterns under certain conditions. The pattern rotates at a nearly constant speed, which is different from the orbital speeds of individual stars. This difference means that the arms do not shear apart quickly, but instead can last for hundreds of millions of years. In Messier 51 measurements of the positions and ages of star-forming regions provide evidence that the arms are indeed long-lived patterns rather than temporary features. Observations of the whirlpool in multiple wavelengths allow astronomers to test predictions of density wave theory. For example, the theory predicts that gas entering the arms will be compressed, leading to the formation of molecular clouds. These clouds should then collapse to form stars which will ionize the surrounding gas. The sequence is therefore gas compression, cloud formation, star birth, and ionization. In practice, this is seen as dust lanes on the inner edges of arms, followed by bright knots of H2 regions further along. In Messier 51, this sequence is clear dust lanes mark where gas is being compressed, and just downstream glowing regions of ionized hydrogen mark where stars have recently formed. This spatial offset provides direct observational support for density wave theory. The pattern speed of the density wave is another key parameter. Astronomers measure pattern speed by comparing the distribution of stars of different ages with the rotation of the disk. If the wave is too slow or too fast, the sequence of star formation would not align with observations. In the whirlpool, estimates of pattern speed are consistent with the observed arrangement of dust gas and young stars. These measurements show that the density wave rotates in such a way that gas entering the arms is compressed at the correct points to sustain ongoing star formation. The agreement between prediction and observation makes the whirlpool one of the strongest cases supporting density wave theory. The role of the companion galaxy adds complexity to the picture. While density wave theory can explain spiral arms in isolated galaxies, external perturbations can also drive spiral patterns. In the case of Messier 51, the close passage of NGC 5195 may have triggered or amplified the density wave. Simulations of galactic interactions show that a smaller companion can generate waves in the disk of a larger galaxy, which then take the form of spiral arms. In this sense, the whirlpool may be both an example of a self-sustained density wave and a tidally induced structure. The presence of a close companion provides an external force that maintains the symmetry and strength of the arms over long timescales. The density wave not only shapes the structure of the disk but also influences the overall rate of star formation. By continuously compressing gas into molecular clouds, the wave ensures a steady supply of new stars. This prevents star formation from being too random or scattered, instead channeling it into organized patterns along the arms. In Messier 51, the star formation rate is elevated compared to similar isolated galaxies, consistent with the idea that both density waves and tidal interactions enhance the process. The whirlpool thus becomes a laboratory for studying how large-scale dynamics control small-scale star formation. Magnetic fields also interact with density waves. Radiopolarization studies show that magnetic lines of force are aligned along the spiral arms. This suggests that as gas is compressed by the wave, the magnetic field is also compressed and ordered. The alignment of magnetic fields can affect how gas clouds collapse, influencing the efficiency of star formation. In Messier 51, the correlation between polarized radio emission and the spiral pattern is strong, showing that magnetic fields are an integral part of the density wave process. This adds another layer of complexity where gravity-gas dynamics and magnetic forces work together to shape the galaxy. The concept of resonance is important in density wave theory. Resonances occur when the orbital frequencies of stars match or relate to the pattern speed of the wave. At these points, the influence of the wave is stronger, and structures such as rings can form. In the Whirlpool, observations of its inner regions suggest that resonances may be present, shaping the distribution of gas and stars near the center. By mapping the kinematics of stars and gas, astronomers attempt to identify the locations of these resonances, which provide further constraints on the dynamics of the density wave. Another test of density wave theory comes from comparing the ages of star clusters along the arms. If the arms are long-lived patterns, clusters should show a sequence of ages as the wave moves through the disk. Younger clusters should be found just downstream of the dust lanes, while older clusters should be further along. In Messier 51, such age gradients have been observed, supporting the idea that the arms are not transient features, but persistent density waves guiding the birth and evolution of stars. These detailed observations strengthen the case that the Whirlpool is one of the clearest examples of a galaxy shaped by density wave dynamics. The Whirlpool Galaxy therefore provides not only a visual example of a grand spiral, but also a quantitative test of density wave theory. Its nearly face-on orientation, clear dust lanes, bright star-forming regions, and close companion combine to create an ideal system for study. By analysing the offsets between dust gas and young stars, measuring pattern speed and comparing simulations, astronomers gain confidence in the theory. At the same time, the role of tidal forces ensures that the system remains an active area of research, showing how external and internal processes can interact to maintain spiral structure. Gravitational tides play a central role in shaping the Whirlpool Galaxy and its smaller companion. When two galaxies come close to one another, their mutual gravity stretches and distorts their structures. This stretching is not uniform. The side of one galaxy that faces the other feels a stronger pull than the far side. The difference in force creates what is called a tidal effect, drawing out material into bridges and tails. In Messier 51, these effects are visible in the faint stream that links it with NGC 5195 and in the subtle warps and asymmetries in its outer disk. The presence of these structures shows that the two galaxies are engaged in an active gravitational encounter, rather than being unrelated objects in the same line of sight. The Whirlpool's stellar orbits reveal signatures of tidal perturbations. In an undisturbed spiral, stars and gas follow relatively stable circular orbits around the galactic center. In an interacting system, these paths are altered. Some stars are pulled into elongated orbits, while gas is shifted outward or inward depending on the local gravitational gradient. Spectroscopic measurements show variations in velocity across the Whirlpool's disk, consistent with the influence of its smaller neighbour. These variations are not random noise but coherent distortions that match predictions of tidal theory. They provide strong evidence that the companion is not merely nearby, but is physically interacting with the larger galaxy. The bridge between the two galaxies is particularly informative. Observations show that it contains both stars and gas, which indicates that the tidal forces have been strong enough to strip matter directly from the Whirlpool, and perhaps also from the companion. The stars in the bridge will continue their orbits around the larger system, while the gas may collapse to form new stars. This process demonstrates how gravitational tides can both remove material from galaxies and stimulate new activity in the process. The existence of star-forming regions along the bridge suggests that the encounter is not only disruptive, but also creative, reshaping the distribution of matter and giving rise to new generations of stars. Tidal tails are another common outcome of galaxy encounters. In the Whirlpool, faint extensions of light can be seen stretching beyond the main disk. These tails are less prominent than in some other interacting galaxies such as the antennae, but they still record the history of close passage. Deep imaging reveals streams of stars that arc away from the disk, evidence of the paths along which material has been pulled out. Such features are difficult to see without sensitive instruments, but once detected they provide a timeline of the interaction, since the length and shape of tails depend on the strength and duration of the gravitational encounter. Models of the Whirlpool system attempt to reproduce these tidal features. By adjusting the mass ratio, orbital parameters, and timing of the encounter simulations, can generate structures similar to the observed bridges and tails. In many models, the companion has passed through or very near the disk of the whirlpool in the recent past, on the order of a few 100 million years ago. This close passage would have been sufficient to excite strong density waves, creating the symmetric arms, and to draw out the streams of material that are observed today. The success of these models in matching observations supports the idea that gravitational tides are the driving force behind the whirlpool's striking appearance. The influence of tidal forces is not limited to the outer disk. They also affect the central regions of galaxies by funneling gas inward. As orbits are perturbed, gas clouds lose angular momentum and spiral toward the center. In the Whirlpool observations of its core show evidence of such inflow. Concentrations of molecular gas have been detected in the central kiloparsec consistent with material being driven inward by the tidal interaction. This inward flow can fuel both starbursts in the inner disk and activity near the galactic nucleus. The presence of a weak active galactic core in Messier 51 may be connected to this process. Thus, the tidal encounter shapes not only the outer arms and bridges, but also the conditions in the core. The companion galaxy is itself altered by tides. NGC 5195 appears distorted, lacking the regular shape of a stable system. Its outer layers are stretched and streams of material are pulled toward the whirlpool. The gas within it is compressed, leading to active star formation that would not be as vigorous if the galaxy were isolated. In this way, the smaller companion is both a source of disturbance and a victim of the same forces. The mutual nature of the interaction highlights how even a massive system like the whirlpool is not immune to the effects of a much smaller partner. Gas dynamics under tidal forces create shocks in the interstellar medium. As gas clouds are pulled along new paths, they collide and compress, triggering bursts of star formation. This process is evident in the whirlpool, where lines of young star clusters are observed along the arms and in the bridge. These clusters are often only a few million years old, indicating that they formed as a direct result of the ongoing interaction. Observing these clusters allows astronomers to link the physics of tidal perturbations to the outcomes of stellar birth, connecting large-scale gravitational dynamics to small-scale astrophysical processes. The timescale of tidal encounters is long by human standards, but relatively short in cosmic terms. The current appearance of the whirlpool is the result of an encounter that has unfolded over a few 100 million years. The system will continue to evolve with the companion orbiting and possibly merging with the larger galaxy over the next billion years or more. During this time, additional passes will create new bridges and tails, further modifying the structure. By studying the whirlpool today, astronomers capture a snapshot in an ongoing process of galactic evolution, a process governed by gravity, and evident in the fine details of bridges, tails, and distorted orbits. Gravitational tides are therefore essential for understanding the whirlpool system. They explain the presence of bridges, the distortion of orbits, the enhancement of star formation, and the inflow of gas to the center. Observations across multiple wavelengths combined with simulations reveal a coherent picture of how the encounter between Messier 51 and NGC 5195 has shaped both galaxies. The whirlpool's grand design spiral arms, its streams of stars, and its active regions of star formation are all linked to the invisible but powerful pull of tides. Dust lanes are among the most distinctive features of the Whirlpool Galaxy. When observed in visible light, the spiral arms are traced not only by bright stars and glowing nebulae, but also by dark filaments that cut across the luminous background. These filaments are concentrations of interstellar dust mixed with gas. The dust particles are tiny, composed mainly of silicates, carbon compounds and ices, and they absorb and scatter starlight. Although the dust accounts for only a small fraction of the galaxy's total mass, its effect on the appearance of the galaxy is significant. In Messier 51, the dust lanes mark the inner edges of the spiral arms, creating sharp contrasts between dark streaks and bright stellar regions. The arrangement of dust lanes provides evidence for the processes shaping the whirlpool's arms. As gas flows into a density wave, it is compressed. This compression enhances the formation of molecular clouds which contain both gas and dust. The dust then becomes concentrated along the inner boundaries of the spiral arms. These dense regions block the light from stars behind them, producing the visible dark bands. This alignment matches predictions of density wave theory, which states that shocks occur on the upstream side of the arms relative to the direction of rotation. In the whirlpool, the observed geometry of the dust lanes fits this model, offering direct support for the idea that spiral arms are waves of compression moving through the disk. Observations in infrared light reveal the dust in greater detail. Dust that absorbs visible starlight is warmed and re-radiates in the infrared. Telescopes such as Spitzer and the Infrared Space Observatory have mapped the dust emission of Messier 51, showing the same spiral pattern visible in optical light, but with additional clarity in regions heavily obscured at shorter wavelengths. Infrared images display glowing arcs of dust aligned with the spiral arms, confirming that dust is a pervasive component of the interstellar medium. The temperature of this dust is typically only a few tens of degrees above absolute zero, but it radiates strongly in the mid and far infrared, allowing astronomers to trace its distribution with precision. Dust lanes also correlate with sites of star formation. Within the dark streaks, molecular clouds form, and these clouds are the birthplaces of stars. As the clouds collapse under their own gravity, new stars ignite and begin to emit intense ultraviolet radiation. This radiation ionizes the surrounding hydrogen gas, producing the glowing H2 regions that are observed just downstream from the dust lanes. The sequence from dust lane to star-forming region is repeated all around the arms of the whirlpool. This progression demonstrates the role of dust not just as an obscuring agent, but as a signpost of the regions where gas is dense enough to form new stars. High-resolution images from the Hubble Space Telescope show the dust lanes in remarkable detail. Filaments of dark material wind through the arms in complex patterns, often branching and intersecting. Some filaments extend for hundreds of light years, while others are narrow threads. These structures are shaped by turbulence, magnetic fields and gravity, producing a rich variety of forms. By studying these details, astronomers gain insight into the small-scale processes within the interstellar medium. The fine structure of the dust lanes shows that even within the ordered spiral arms, chaotic motions and instabilities play a role in shaping the gas and dust. The presence of dust has important consequences for the measurement of the galaxy's properties. Dust absorption dims the light of stars, making them appear fainter than they would without obscuration. This must be corrected when estimating distances, luminosities, and star formation rates. In the whirlpool, the nearly face-on orientation minimizes the effect compared to edge-on galaxies where dust lanes can block large fractions of starlight. Even so, corrections are required particularly in regions near the spiral arms where dust is thickest. Infrared and radio observations help by providing alternative measures that are less affected by dust absorption. Dust also affects the chemistry of the interstellar medium. The surfaces of dust grains provide sites where atoms can stick together and form molecules. For example, molecular hydrogen, the most abundant molecule in the universe, forms primarily on dust grain surfaces. Without dust, the formation of molecular clouds would be far less efficient. In this way, dust is essential for the cycle of star formation. In Messier 51, the abundance of dust lanes indicates that the galaxy has a robust supply of sites for molecule formation supporting its high rate of star formation. Polarization studies add another dimension to the study of dust. Light passing through dust can become polarized if the dust grains are aligned by magnetic fields. Observations of polarized starlight in the Whirlpool reveal patterns that trace the magnetic field lines threading the spiral arms. These studies show that dust is not randomly oriented but interacts with large-scale magnetic structures. The alignment provides information about both the dust itself and the forces shaping the interstellar medium. By combining optical polarization with radio polarization, data astronomers build a more complete picture of the magnetic and dusty environment of the galaxy. The role of dust lanes in the Whirlpool is therefore multifaceted. They are visual tracers of density waves, markers of star formation, sources of infrared emission sites of molecular chemistry, and probes of magnetic fields. Their presence emphasizes the importance of interstellar dust in galactic evolution. While dust is only about 1% of the interstellar medium by mass, it governs how galaxies look in visible light and how stars form from gas. In Messier 51, the prominence of the dust lanes makes these processes clear to observation, providing a laboratory for understanding the interplay between gas dust and stars. Star-forming regions in the Whirlpool Galaxy are among its most striking features. Along the spiral arms, bright knots stand out where hydrogen gas glows in red emission lines. These knots are H2 region zones of ionized hydrogen, surrounding clusters of young massive stars. The ultraviolet radiation from these hot stars strips electrons from the hydrogen atoms, causing the gas to shine as the electrons recombine. The result is a chain of luminous patches that trace the paths of the spiral arms in optical images. The prevalence of these regions demonstrates that the Whirlpool is an actively star-forming galaxy, with large amounts of gas being converted into new stars. The size and brightness of H2 regions in Messier 51 vary. Some are small and faint, representing individual clusters of stars, while others span hundreds of light years and represent giant complexes of star formation. The largest of these regions rival the Orion Nebula in the Milky Way, but on a much larger scale. Observations show that the distribution of these star-forming complexes is not random, but follows the density wave pattern of the spiral arms. The gas is compressed as it enters the arms, collapses into clouds, and rapidly forms stars which then light up the surrounding gas. This sequence produces a repeating pattern of dust lanes, followed by glowing H2 regions along the arms. Spectroscopic studies provide further detail. The emission lines of hydrogen, oxygen, nitrogen, and sulfur in the H2 regions allow astronomers to measure the chemical composition of the gas. In Messier 51, the metallicity, meaning the abundance of elements heavier than helium, is relatively high, consistent with its status as a large evolved spiral galaxy. The distribution of metallicity varies with radius declining outward from the center. This gradient reflects the history of star formation, since repeated generations of stars enrich the gas with heavy elements over time. By studying the metallicity of the Whirlpool's H2 regions, astronomers can trace how chemical enrichment has proceeded across the disk. The ages of stellar clusters in the Whirlpool provide another line of evidence. Young clusters are found close to the dust lanes, while slightly older clusters are located further downstream in the arms. This spatial arrangement reflects the progression of star formation as gas enters the density waveform stars and then moves out of the compression zone. In some cases, clusters are only a few million years old, while in others they are tens of millions of years old. This sequence demonstrates that the arms act as star-forming engines, continuously generating new populations of stars as material passes through. The clarity of this pattern in Messier 51 makes it an important system for testing theories of spiral structure and star formation. Infrared observations reveal embedded star-forming regions that are hidden from view in optical light. Dust absorbs visible radiation but allows infrared to pass through. Telescopes such as Spitzer and Herschel have mapped the whirlpool in the infrared, showing luminous knots of warm dust where stars are forming inside dense clouds. These observations confirm that much of the star formation activity is obscured in visible images. By combining optical and infrared data, astronomers obtain a more complete census of star-forming regions. In Messier 51, the rate of star formation is estimated to be several solar masses per year, comparable to or somewhat higher than that of the Milky Way. Radio observations add another dimension by tracing molecular gas, the raw material for star formation. Emission from carbon monoxide, a common tracer of molecular hydrogen, maps the locations of giant molecular clouds in the whirlpool. These clouds are aligned with the dust lanes, supporting the idea that compression in the spiral arms transforms diffuse gas into dense molecular clouds. The masses of these clouds can be enormous, reaching millions of solar masses. Within them, clusters of stars form, giving rise to the luminous H2 regions observed downstream. By studying the distribution and properties of these clouds, astronomers understand how the cycle of star formation is maintained. The feedback from young stars also plays a role in shaping the interstellar medium. Massive stars emit strong winds and eventually explode as supernovae, injecting energy and heavy elements into their surroundings. In Messier, 51 bubbles and shells of gas are observed around some star-forming regions, evidence of this feedback. These structures can trigger secondary star formation by compressing nearby gas, or they can disrupt clouds and halt further collapse. The balance between triggering and disruption influences the overall efficiency of star formation in the galaxy. The whirlpool provides numerous examples of this feedback in action, visible across its arms. The distribution of star formation in the whirlpool is not limited to the spiral arms. Observations show enhanced activity near the bridge connecting the galaxy to its companion. This suggests that tidal forces from the interaction are also stimulating star formation outside the main disk. The companion galaxy itself hosts regions of active star formation, further demonstrating the mutual influence of the two systems. The interaction therefore enhances star formation both within the whirlpool and in its smaller neighbour. This provides a clear case of how gravitational encounters can drive bursts of star formation across entire galaxies. High-resolution imaging from the Hubble Space Telescope has allowed individual stellar clusters in Messier 51 to be catalogued and studied. Thousands of clusters are identified spanning a wide range of ages and masses. These clusters provide a record of the galaxy's star formation history. The youngest clusters are associated with the bright H2 regions, while older clusters are spread more evenly across the disk. By analyzing the colors and brightness of these clusters, astronomers reconstruct the timeline of star formation events. In the whirlpool, this timeline shows a close connection between episodes of enhanced star formation and the interaction with the companion galaxy. The study of star-forming regions in the whirlpool informs broader questions about galaxy evolution. It shows how spiral arms organize gas into clouds, how interactions trigger bursts of activity, and how feedback from young stars regulates the process. The clarity and abundance of H2 regions in Messier 51 make it a benchmark system for calibrating models of star formation. By examining these glowing knots of ionized gas, astronomers link the largest scales of galactic dynamics to the smallest scales of stellar birth, creating a comprehensive picture of how galaxies sustain their stellar populations. The interstellar medium of the Whirlpool Galaxy is composed of several distinct phases, each representing a different state of gas and dust spread across the disk. These phases include atomic gas molecular clouds, ionized gas, and interstellar dust. Together they form the raw material from which stars are born, and into which stars return mass through winds and supernova explosions. Understanding the balance of these components is essential for interpreting the galaxy's structure and evolution. In Messier 51, the interplay between these phases is visible with unusual clarity because of the nearly face-on orientation, which allows astronomers to trace their distribution across the spiral arms. Atomic hydrogen is one of the most widespread components of the interstellar medium. It is detected by its emission at a wavelength of 21 centimeters in the radio band. Large radio dishes and interferometers map this emission, revealing the distribution of neutral hydrogen across the whirlpool. These observations show that the atomic gas extends far beyond the visible disk of stars, forming an envelope that reaches into the outskirts of the system. This outer gas acts as a reservoir for future star formation. The velocity of the hydrogen emission also provides information on the galaxy's rotation, helping to trace the gravitational potential and to infer the presence of dark matter. Molecular gas is more concentrated and is the direct precursor of star formation. Because molecular hydrogen is difficult to observe directly, astronomers use carbon monoxide as a tracer since it emits strongly at millimeter wavelengths. Observations with instruments such as the Atacama Large Millimeter Array and earlier radio telescopes have mapped the carbon monoxide distribution in Messier 51. The molecular gas is concentrated along the dust lanes of the spiral arms, where density waves compress the atomic gas and convert it into molecular form. These molecular clouds are the sites where stars are born, and their masses can range from thousands to millions of solar masses. In the whirlpool, the correlation between molecular gas and star-forming regions is strong, supporting the picture of spiral density waves driving the cycle of star formation. Ionized gas is present in the form of H2 regions around young massive stars. This gas is visible in optical emission lines, particularly the hydrogen alpha line at 656 nanometers. Surveys of the whirlpool in this line reveal a chain of bright knots tracing the spiral arms. These regions represent the immediate environment of newborn stars where the interstellar medium is heated and ionized by intense radiation. The distribution and brightness of these knots provide information about the rate of star formation and the clustering of young stars. In Messier 51, the abundance of such regions demonstrates that star formation is proceeding vigorously across the disk. Dust is another key component of the interstellar medium. Although it constitutes only about 1% of the total mass, it has a disproportionate effect on the appearance and physics of the galaxy. Dust grains absorb and scatter visible light, creating the dark lanes seen in optical images. They also re-radiate energy in the infrared, making them visible to telescopes operating at longer wavelengths. In the whirlpool, dust emission has been mapped by the Spitzer and Herschel space telescopes, showing arcs and filaments aligned with the spiral arms. Dust grains also serve as catalytic surfaces for the formation of molecules, making them essential for the chemistry of the interstellar medium. These different phases are not isolated but interact continuously. Atomic gas condenses into molecular clouds in the spiral arms. Molecular clouds collapse to form stars whose radiation then ionizes the surrounding gas. Supernovae and stellar winds inject energy back into the interstellar medium, heating and dispersing gas and dust. This cycle sustains the evolution of the galaxy. In Messier 51, the interaction with the companion galaxy adds further complexity by stirring the interstellar medium and triggering additional compressions. The result is a dynamic system in which gas is constantly moving between phases and regions. Multi-wavelength observations are necessary to capture the full picture. Optical telescopes reveal ionized gas and dust lanes. Infrared instruments detect warm dust and embedded star formation. Radio telescopes map atomic and molecular gas. Ultraviolet observations highlight young hot stars, while X-ray telescopes detect hot plasma from supernova remnants and binary systems. When combined, these datasets provide a layered view of the interstellar medium in the whirlpool. For example, comparing radio maps of molecular gas with optical images of H2 regions shows the progression from gas to stars. Infrared maps then reveal the dust heated by these young stars. This comprehensive approach allows astronomers to study the life cycle of gas and stars in detail. The mass distribution among the phases offers insight into the efficiency of star formation. In the whirlpool, a significant fraction of the interstellar medium is in the form of molecular gas, reflecting the high rate of star formation. The presence of abundant dust lanes supports this conclusion, since dust traces dense molecular clouds. Atomic gas dominates the outer regions where densities are lower and star formation is less active. The balance between these components is shaped both by internal processes such as density waves and by external influences from the companion galaxy. By measuring the relative amounts of atomic, molecular, and ionized gas, astronomers assess how effectively the whirlpool is turning its raw material into stars. The physical conditions of the interstellar medium also vary across the galaxy. In the spiral arms, gas densities are higher, and temperatures are moderate, favoring the formation of molecular clouds. In the interarm regions, densities are lower, and much of the gas remains atomic. Near star-forming regions, the gas is ionized and heated to thousands of degrees. Supernovae and stellar winds can produce bubbles of hot plasma, with temperatures of millions of degrees detectable in X-rays. These hot phases fill cavities in the disk, while colder phases dominate along the arms. The coexistence of these phases reflects the turbulent and dynamic nature of the interstellar medium. The Whirlpool Galaxy therefore provides a detailed example of the multi-phase structure of the interstellar medium. Its nearly face-on orientation, active star formation, and ongoing interaction with a companion make the different phases easy to observe and compare. By studying atomic gas molecular clouds, ionized regions and dust, astronomers piece together the complex cycle that governs the life of galaxies. The whirlpool serves as a natural laboratory where the physics of gas, dust, and stars can be investigated in detail, yielding insights that apply broadly to spiral galaxies across the universe. Magnetic fields in the Whirlpool Galaxy are not visible to the eye, yet they form a significant part of its structure. These fields are detected through observations of polarized radio emission, a technique that measures the orientation of light waves emitted by electrons spiraling around magnetic field lines. When astronomers map the polarized emission across Messier 51, they find that the magnetic fields align closely with the spiral arms. The fields are ordered and coherent, following the same sweeping curves traced by dust lanes and star-forming regions. This alignment suggests that magnetic fields are not random, but are shaped by the dynamics of the galaxy, particularly the density waves that compress gas and dust. The strength of the magnetic fields in the whirlpool is estimated to be several microgauss, comparable to the magnetic field in the Milky Way. While this field is weak compared to magnets used on Earth, it is sufficient to influence the behavior of gas across interstellar distances. Magnetic pressure helps to support clouds against gravitational collapse, while at the same time guiding the flow of charged particles. The interaction between magnetic fields and gas dynamics is complex. In regions where the density wave compresses material, the magnetic field is also compressed, becoming stronger and more ordered. This explains the close alignment between magnetic fields and spiral arms. Radiopolarization maps reveal both the ordered and turbulent components of the magnetic field. The ordered component runs parallel to the arms, while the turbulent component is associated with star-forming regions, where stellar winds and supernova stir the gas. In Messier 51, the balance between these two components varies with location. Along the major arms, the ordered field dominates, producing long stretches of aligned polarization vectors. In the interarm regions, turbulence is more evident, and the polarization is less coherent. This distribution shows how large-scale structure and local processes combine to shape the magnetic environment of the galaxy. The study of magnetic fields in the Whirlpool has been advanced by high-resolution observations from the Carl G. Jansky Very Large Array and the Effelsberg Radio Telescope. These instruments provide detailed maps of polarized emission across the disk. The results show that the magnetic field is not simply a passive tracer, but plays an active role in the evolution of the interstellar medium. For example, magnetic fields can channel cosmic rays, which are high-energy particles traveling near the speed of light. The motion of these particles along field lines contributes to the heating and ionization of the gas. In Messier 51, the correlation between cosmic ray emission and magnetic field structure highlights this interaction. The role of magnetic fields in star formation is a subject of ongoing study. In molecular clouds, magnetic pressure can counteract gravity delaying collapse. However, magnetic fields can also guide the inflow of material, making collapse more efficient once it begins. Observations of polarized dust emission in star-forming regions of the Whirlpool suggest that magnetic fields are indeed shaping the collapse of clouds. The fields are often aligned with the elongation of the clouds, indicating that they influence the direction of fragmentation and starbirth. By comparing these observations with simulations, astronomers seek to determine how magnetic fields regulate the rate of star formation in galaxies. Faraday rotation provides another method for probing magnetic fields. As polarized radio waves pass through ionized gas, their plane of polarization rotates by an amount proportional to the strength of the magnetic field along the line of sight and the density of electrons. Measurements of Faraday rotation in Messier 51 confirm the presence of coherent magnetic fields across the disk. These measurements also reveal reversals in the direction of the field in some regions, which may result from dynamo processes generating magnetic fields within the rotating galaxy. Such reversals are important for understanding how large-scale galactic magnetic fields are maintained. The connection between magnetic fields and spiral density waves is particularly clear in the Whirlpool. As the wave compresses gas and dust, it also compresses magnetic fields, leading to enhanced polarization along the arms. In some cases, the magnetic field appears to extend slightly beyond the optical arm, suggesting that magnetic forces may influence gas even outside the main compression zone. This observation supports the idea that magnetic fields are dynamically significant, not just passive features. They may help to maintain the coherence of the spiral pattern by coupling the motions of gas across large regions of the disk. The companion galaxy, NGC 5195, also affects the magnetic environment. The gravitational interaction that drives density waves in the Whirlpool stirs the interstellar medium, stretching and amplifying magnetic fields. Simulations suggest that tidal encounters can increase the strength of galactic magnetic fields by winding them up and compressing them in certain regions. In Messier 51, the ordered structure of the fields, despite the ongoing interaction, indicates that magnetic forces are resilient and capable of reorganizing themselves even in disturbed conditions. This resilience may help explain why magnetic fields are observed in galaxies across a wide range of environments. Cosmic rays provide an indirect measure of magnetic activity. These energetic particles emit synchrotron radiation as they spiral around magnetic field lines. The intensity and polarization of this emission depend on both the number of particles and the field strength. In the Whirlpool synchrotron emission traces the spiral arms, further confirming the close relationship between magnetic fields and the large-scale structure of the galaxy. By comparing synchrotron emission with thermal emission, from ionized gas, astronomers separate the contributions of magnetic and non-magnetic processes. The result is a comprehensive map of how magnetic fields, cosmic rays, and gas interact. The Whirlpool Galaxy therefore serves as an important laboratory for the study of galactic magnetism. Its nearly face-on orientation allows the magnetic field structure to be mapped with exceptional clarity. The alignment of fields with spiral arms, the evidence for compression by density waves, the interaction with cosmic rays, and the signatures of dynamo processes all combine to provide a detailed picture of magnetic phenomena in a galaxy. These observations show that magnetic fields are integral to the dynamics of galaxies, influencing gas motion, star formation, and cosmic ray propagation. Messier 51 illustrates how invisible forces shape the visible structure of the universe. Observations of the Whirlpool Galaxy across multiple wavelengths reveal different aspects of its structure and activity. In optical light, the face-on spiral arms dominate the view with bright knots of young stars and glowing nebulae outlined by dark dust lanes. This is the view first captured in sketches and photographs, and it remains the most familiar. However, optical light only samples part of the galaxy, mainly the starlight that can penetrate the dust and the emission lines from ionized gas. To gain a complete understanding of Messier 51, astronomers use instruments sensitive to ultraviolet infrared radio and X-ray radiation, each highlighting a different component of the system. Ultraviolet observations emphasize the youngest and hottest stars. These stars emit most of their energy in ultraviolet wavelengths, which are absorbed by Earth's atmosphere and must be observed from space. Telescopes such as the Galaxy Evolution Explorer have imaged Messier 51 in ultraviolet, showing luminous ribbons along the spiral arms. These ribbons mark the locations of recent star formation, often aligning with the dust lanes where gas is compressed. In ultraviolet, the arms appear sharper and more continuous since young stars dominate the emission. The central bulge appears fainter because older stars emit less ultraviolet radiation. This wavelength provides a direct tracer of star formation over the past few 100 million years. Infrared observations reveal cooler structures that are hidden in optical light. Dust grains heated by starlight emit in the infrared, and embedded star-forming regions glow brightly at these wavelengths. Instruments such as the Spitzer Space Telescope and the Herschel Space Observatory have mapped the whirlpool in mid and far infrared. The resulting images show arcs of warm dust tracing the spiral arms and clumps of emission where new stars are forming inside molecular clouds. Far infrared data are particularly useful for estimating the total star formation rate, since they capture the reprocessed light from dust that obscures many regions in visible wavelengths. In Messier, 51 infrared measurements confirm that the galaxy is actively forming stars at several solar masses per year. Radio observations provide information about the coldest components of the interstellar medium. Neutral hydrogen is detected through its emission at 21 centimeters, revealing a disk that extends beyond the visible stars. This disk shows signs of tidal disturbance from the companion galaxy, with streams of gas connecting the two systems. Molecular gas traced by carbon monoxide is concentrated along the dust lanes of the spiral arms. These radio maps show where giant molecular clouds are located and how they relate to the optical and infrared images. Radio observations also detect synchrotron emission from cosmic rays spiraling around magnetic field lines, providing insight into the strength and orientation of galactic magnetic fields. In Messier 51, synchrotron emission outlines the spiral structure, confirming the alignment of magnetic fields with the arms. X-ray observations probe the hottest and most energetic processes in the Whirlpool. The Chandra X-ray Observatory has imaged Messier 51, revealing a population of compact sources such as neutron stars and black holes accreting matter. These objects emit high-energy radiation as gas falls onto their surfaces or into their event horizons. Supernova remnants also shine in X-rays, marking the deaths of massive stars. Diffuse emission from hot gas pervades some regions, filling cavities created by stellar winds and explosions. In the central region of Messier, 51 X-ray data suggest the presence of a weak active nucleus, where a supermassive black hole may be accreting gas at a low rate. These high-energy observations complete the picture by showing the end stages of stellar evolution and the feedback of massive stars into the interstellar medium. The combination of all these wavelengths creates a layered view of the galaxy. Optical images show stars and glowing gas. Ultraviolet traces young stellar populations. Infrared highlights dust and embedded star formation. Radio maps cold gas and magnetic fields, and X-rays reveal compact remnants and hot plasma. Each wavelength alone provides only a partial perspective, but together they allow astronomers to reconstruct the full life cycle of gas and stars. In Messier 51, the alignment of features across different bands supports the density wave model of spiral arms. Dust lanes in optical images correspond to molecular gas in radio maps, and to warm dust in infrared images. Ultraviolet ribbons of young stars align just downstream, followed by X-ray sources that represent the remnants of massive stars born in those same regions. Multi-wavelength studies also refine measurements of star formation rates. In optical light, dust absorption can cause underestimates, since much of the light from young stars is hidden. Infrared data correct for this by capturing the re-emitted energy. Radio observations provide estimates of molecular gas mass, allowing astronomers to calculate how efficiently gas is being converted into stars. Ultraviolet observations trace star formation over slightly longer timescales, while X-rays reveal the end products of massive stars. In the Whirlpool, these complementary methods converge on a consistent picture of active sustained star formation, driven by density waves and tidal interaction. The central region of the Whirlpool benefits particularly from multi-wavelength observations. In optical light, the core appears as a bright bulge of older stars. Infrared data reveal dust and gas concentrated around the nucleus, while radio maps show inflows of molecular gas possibly driven by tidal forces. X-rays detect a compact source consistent with a supermassive black hole accreting matter. Ultraviolet observations show little activity in the center, since older stars dominate there. By combining all these data, astronomers conclude that Messier 51 hosts a low-luminosity active galactic nucleus, not bright enough to dominate the galaxy's emission, but detectable when viewed in high-energy bands. The companion galaxy NGC 5195 is also examined in multiple wavelengths. In optical light, it appears as a faint, irregular object. In infrared, it shows patches of warm dust corresponding to active star-forming regions. Radio maps reveal gas stripped into the bridge connecting it to the whirlpool. X-rays detect a few compact sources, likely the remnants of massive stars formed in recent bursts of activity. The differences between the companion and the main galaxy illustrate how tidal interactions can stimulate star formation even in small systems, while also distorting their structures and redistributing their gas. The Whirlpool Galaxy thus exemplifies the value of observing the universe across the electromagnetic spectrum. No single wavelength provides a complete account of the processes at work. Only by combining data from ultraviolet to radio, from infrared to X-rays, can astronomers piece together the intricate balance of gas-dust stars and compact objects. In Messier 51, this comprehensive approach transforms the view of a beautiful spiral into a detailed understanding of the physics driving its evolution. The central region of the Whirlpool Galaxy is an area of particular interest, because it contains the nucleus where the most massive structures and oldest stellar populations are found. In visible light, the center appears as a bright bulge surrounded by the tightly wound beginnings of spiral arms. This bulge contains primarily older stars with relatively little new star formation compared to the arms. Spectroscopic studies of the light from this region reveal the signatures of evolved stellar populations, including red giants and other long-lived stars. These populations dominate the optical brightness of the central bulge, giving it a smooth yellowish appearance. Infrared observations provide further insight into the central region. Infrared light penetrates the dust that obscures parts of the nucleus in optical images, revealing structures hidden in visible wavelengths. Instruments such as the Spitzer Space Telescope and the infrared camera on the Subaru telescope show concentrations of warm dust and molecular gas within the inner kiloparsec. This material is thought to be funneled toward the center by gravitational torques induced by the spiral density waves and the interaction with the companion galaxy. The inflow of gas may provide fuel for both star formation and nuclear activity. Radio observations detect molecular gas concentrated in circumnuclear rings. Carbon monoxide mapping reveals dense clouds orbiting within a few hundred parsecs of the center. These rings are interpreted as the result of resonances in the galactic potential, where gas is trapped and compressed. The inflow of gas from the outer disk encounters these resonances, causing it to accumulate in specific zones, rather than falling directly into the nucleus. This process both regulates the supply of gas to the central black hole and provides conditions suitable for forming new stars in the inner disk. Observations of hydrogen cyanide and other dense gas traces confirm that the nucleus of Messier 51 is rich in star-forming material. X-ray data from the Chandra Observatory show that the whirlpool hosts a compact central source. This source is interpreted as a low-luminosity active galactic nucleus powered by accretion onto a supermassive black hole. The X-ray emission is weak compared to bright quasars or Seyfert galaxies, but it is consistent with the presence of a black hole of several million solar masses accreting at a low rate. In addition to the compact source, diffuse X-ray emission fills the central region produced by hot gas heated by supernova explosions and stellar winds. The coexistence of weak nuclear activity and vigorous stellar processes illustrates the complexity of the inner whirlpool. Ultraviolet observations of the center show relatively little emission compared to the arms. This indicates that massive young stars are not abundant in the nucleus. Instead, the ultraviolet light detected there is attributed mainly to older populations such as horizontal branch stars. The lack of strong ultraviolet emission supports the view that the central bulge is dominated by an older stellar population, in contrast to the youthful arms rich in star-forming regions. This difference between the center and the arms highlights the diverse environments present within a single galaxy. Kinematic studies provide information about the motions of stars and gas in the nucleus. Spectra reveal broadened absorption lines from stars indicating that they move with high random velocities typical of bulge populations. Gas motions are more complex, showing inflow and rotation influenced by non-axis symmetric structures such as bars or spiral patterns. Measurements of these motions are used to estimate the mass of the central black hole through the stellar velocity dispersion method. Results for Messier 51 suggest a black hole of several million solar masses, consistent with the presence of a faint active nucleus. The interplay between stellar dynamics, gas inflow, and black hole accretion defines the behavior of the central region. Circumnuclear star formation is observed in rings around the nucleus. Optical and infrared imaging shows clusters of young stars located a few hundred parsecs from the center. These clusters are thought to form where inflowing gas accumulates at resonances, creating conditions of high density that favor star formation. The rings of clusters provide evidence that even in the inner galaxy, the cycle of star formation continues, though in a more organized and restricted pattern than in the arms. The balance between feeding the black hole and forming new stars depends on how much gas is funneled inward and how it is distributed. The nuclear spectrum of Messier 51 also shows emission lines characteristic of ionized gas. These lines indicate that radiation from the central black hole or from shocks in the gas is energizing the surrounding medium. The classification of the nucleus varies in the literature, with some studies describing it as a low ionization nuclear emission line region, or LINER, while others classify it as a safer Type II nucleus. In either case, the activity is relatively weak, suggesting that the black hole is currently accreting at a fraction of its maximum possible rate. The variability of the emission over time is also studied with changes in the X-ray flux, pointing to fluctuations in the accretion process. The presence of nuclear activity in Messier 51 has implications for understanding how galaxies evolve. The inflow of gas triggered by interactions can both fuel starbursts and activate central black holes. The feedback from these processes in the form of winds and radiation can in turn regulate further inflow and star formation. In the Whirlpool, the active nucleus is modest, but it demonstrates the principle that even grand design spirals with strong star formation in their arms can host black holes influencing their central environments. By studying the nucleus of Messier 51, astronomers link the small-scale physics of accretion disks and black holes with the large-scale dynamics of spiral arms and tidal encounters. The central region of the Whirlpool Galaxy is therefore a complex zone where old stars, new stars, gas inflows, circumnuclear rings, and a weakly active black hole all coexist. Each wavelength of observation adds a piece to this picture, from the optical light of bulge stars to the radio maps of molecular gas, from the X-rays of compact sources to the infrared glow of dust. Together, these observations reveal a nucleus that is not dominated by a bright quasar, but is nonetheless a key element of the galaxy's ongoing evolution. The mass distribution of the Whirlpool Galaxy is studied through its rotation curve, which describes how orbital velocity changes with distance from the center. In a simple system dominated by visible matter, one would expect orbital velocities to decline at large radii following the pattern seen in planetary systems, where the central mass controls the motion. However, in galaxies like Messier 51, observations show that velocities remain nearly constant, or even rise slightly with distance from the center. This discrepancy indicates the presence of additional unseen mass. The concept of dark matter is introduced to explain this, a component that interacts through gravity but not through light. To construct the rotation curve of the Whirlpool, astronomers measure Doppler shifts in the light from stars and gas across the disk. Optical emission lines such as hydrogen alpha provide velocities in the inner regions, while radio observations of the 21 centimeter line of neutral hydrogen extend the measurements to the outer disk. Together, these data produce a detailed profile of how velocity changes with radius. In Messier 51, the curve remains flat well beyond the bright stellar disk, implying that the total mass continues to rise with radius, even where starlight becomes faint. This extended mass is attributed to a dark matter halo encompassing the galaxy. The shape of the rotation curve is influenced not only by dark matter, but also by the distribution of stars and gas. The central bulge contributes significantly to velocities in the inner kiloparsecs. The stellar disk dominates in intermediate regions, while the dark matter halo becomes more important in the outskirts. By modeling the contributions of these components, astronomers can estimate both the mass-to-light ratio of the stellar populations and the density profile of the dark halo. For Messier 51 models suggest that the dark halo is massive and extended, providing most of the gravitational force at large radii. This conclusion aligns with results for many other spiral galaxies, reinforcing the idea that dark matter is a universal component of galactic structure. The mass of the Whirlpool's disk is also estimated from its brightness and stellar populations. By comparing the colors and spectra of stars with models of stellar evolution, astronomers infer how many stars of different masses are present. The resulting stellar mass-to-light ratio allows conversion from luminosity to mass. In Messier 51, the stellar mass is measured to be tens of billions of solar masses, while the gas contributes a smaller but non-negligible fraction. However, the flat rotation curve shows that these visible components alone cannot explain the observed velocities. The total mass implied by dynamics is several times larger than the mass inferred from light, pointing to the dominant role of dark matter. Gravitational interactions with the companion galaxy also influence the Whirlpool's mass distribution. The tidal bridge and tails suggest that material is being redistributed, and simulations require a massive halo to reproduce the observed structures. Without a halo, the disk would be too fragile and would distort more dramatically. The presence of dark matter provides the gravitational glue that stabilizes the disk, while still allowing tidal features to develop. This shows how studies of interactions not only reveal galaxy evolution, but also constrain the properties of dark matter halos. In Messier 51, the relatively gentle nature of the distortions is consistent with a massive extended halo cushioning the effects of the encounter. Dark matter halos are usually described by density profiles that decline with radius. Common models include the Navarro-Frank-White profile and the pseudo-isothermal sphere. For the Whirlpool data are not precise enough to distinguish between models, but the general requirement is clear: the halo must extend well beyond the visible disk and contain more mass than all the stars and gas combined. This invisible component shapes the motion of stars, gas, and even the companion galaxy. Without it, the observed dynamics would be impossible to explain. The rotation curve of Messier 51 also informs understanding of how galaxies form and evolve. Dark matter halos are thought to collapse first in the early universe, drawing in gas that forms the visible galaxy. The Whirlpool's flat rotation curve is evidence of such a halo. By comparing its mass distribution with that of other galaxies, astronomers test theories of cosmological structure formation. The consistency of these results across many systems strengthens the case that dark matter is a fundamental ingredient of the universe. The study of mass distribution also extends to the inner regions of the whirlpool. Stellar velocity dispersions in the bulge provide estimates of the central mass concentration, including the supermassive black hole. Gas motions in circumnuclear rings trace resonances and inflows. These measurements, combined with rotation curves, create a comprehensive picture of mass on scales, from parsecs to tens of kiloparsecs. Messier 51 therefore illustrates how galaxies are held together by a combination of stars, gas, dark matter, and central black holes, each dominating at different scales. The influence of dark matter is not directly observable, but its effects permeate every measurement of galactic dynamics. In the whirlpool, the flat rotation curve, the stability of the disk, the formation of tidal structures, and the behavior of the companion all point to an extended halo. This unseen mass outweighs the luminous matter and shapes the galaxy's future evolution. By studying the distribution of velocities and comparing with models, astronomers derive constraints on the halo's density and extent, contributing to the broader effort to understand the nature of dark matter. The Whirlpool Galaxy's mass distribution thus provides a clear case of the discrepancy between light and mass that defines the dark matter problem. The visible spiral arms and bright star-forming regions represent only the surface features of a much deeper gravitational system. Beneath them lies an unseen halo that binds the galaxy and dictates its dynamics. Observations across optical, radio, and infrared wavelengths converge on this conclusion, making Messier 51 not only a striking spiral, but also a vital piece of evidence in the search to understand the universe's invisible mass. Estimating the distance to the Whirlpool Galaxy has long been a central challenge in astronomy, because distance provides the scale for every other property. If the distance is known, astronomers can calculate the absolute luminosity of stars, the size of the disk, the total mass, and the rate of star formation. If the distance is uncertain, all these derived quantities carry large errors. Over time, methods for measuring cosmic distances have become more precise, and Messier 51 has served as an important case for refining these techniques. One of the earliest reliable methods used for external galaxies is the identification of Cepheid variable stars. These are stars that pulsate in brightness with regular periods. Henrietta Leavitt discovered in the early 20th century that the period of a Cepheid is directly related to its true luminosity. By measuring the period, astronomers can infer the absolute brightness of the star. Comparing this with the apparent brightness observed from Earth gives the distance. In the Whirlpool Galaxy, Cepheid variables have been identified with the Hubble Space Telescope, providing one of the most accurate distance estimates. The results place Messier 51 at approximately 23 million light-years away, or about 7 million parsecs. Other standard candles have also been applied. Type Ia supernovae, which occur when a white dwarf in a binary system accretes enough mass to trigger a runaway explosion, have nearly uniform intrinsic brightness. When a type Ia supernova occurs in a galaxy, it provides a powerful distance indicator. Messier 51 has hosted several supernovae in modern times, including type Ia events that were used to confirm distance estimates based on Cepheids. The agreement between methods strengthens confidence in the measured distance and reduces systematic errors. Planetary nebulae have been employed as secondary distance indicators. These objects, created when dying stars shed their outer layers, have a characteristic luminosity function. By measuring the brightness distribution of planetary nebulae in Messier 51, astronomers obtain another distance estimate. Surface brightness fluctuations, a technique that relies on the graininess of unresolved stars in the bulge of a galaxy, provide yet another method. These approaches all converge on a distance consistent with that from Cepheids and supernovae, reinforcing the reliability of the result. distance measurement is complicated by the effects of dust extinction and crowding. Cepheid variables and other standard candles can appear dimmer than expected if dust in the galaxy absorbs some of their light. High-resolution imaging from space telescopes helps reduce this problem by resolving individual stars and allowing corrections for extinction. Careful analysis of the colors of cepheids provides additional corrections. The Whirlpool's nearly face-on orientation helps as well, since dust lanes obscure less of the stellar population than in edge-on systems. These factors contribute to the accuracy of distance measurements for this galaxy, compared to more inclined spirals. Another check on distance comes from the Tully-Fisher relation, an empirical correlation between the luminosity of a spiral galaxy and its rotational velocity. By measuring the width of the hydrogen line in the Whirlpool spectrum, astronomers determine the galaxy's rotation speed. This is then compared to its luminosity to yield a distance estimate. Although the Tully-Fisher method is less precise than Cepheids or supernovae for a single galaxy, it provides an independent cross-check and is particularly valuable for large surveys where individual stars cannot be resolved. For Messier 51, the Tully-Fisher distance is in reasonable agreement with other methods, adding confidence to the overall picture. Accurate distance to the Whirlpool allows astronomers to calculate its physical size. The disk is measured to be about 60,000 light-years across, smaller than the Milky Way, but still containing hundreds of billions of stars. The thickness of the disk and the extent of its halo are harder to measure directly, but with distance-known angular dimensions can be converted into linear scales. This precision enables comparisons with simulations of interacting galaxies, where orbital parameters depend sensitively on the separation between systems. Without reliable distance models of the interaction with NGC, 5195 would be far more uncertain. Supernovae in Messier 51 not only provide distance indicators, but also serve as probes of stellar populations. Several supernovae have been recorded in this galaxy, including both core collapse events from massive stars and Type A events from white dwarfs. Each explosion has been used to refine distance estimates and to study the chemical enrichment of the galaxy. The visibility of supernovae in Messier 51 is aided by its relative closeness, making it a frequent target for amateur astronomers and professional surveys alike. Each event adds to the body of data that constrains the galaxy's distance and properties. The determination of distance also plays a role in calibrating the cosmic distance ladder. Cepheids in Messier 51 help tie together local measurements with those at greater scales. By anchoring Type Ia supernovae in this galaxy to Cepheid distances, astronomers refine the calibration of supernova luminosities. These calibrated supernovae are then used to measure distances to galaxies much farther away, extending to hundreds of millions or billions of light-years. Thus, the Whirlpool Galaxy is not only an object of interest in itself, but also a stepping stone in measuring the scale of the universe. Future measurements may improve the precision even further. The James Webb Space Telescope, with its sensitivity to infrared light, can observe Cepheids and red giant branch stars with less interference from dust. The tip of the red giant branch method, which uses the luminosity of the brightest red giant stars as a standard candle, is especially effective in the infrared. Applying this technique to Messier 51 could refine its distance to within a few percent. Such accuracy would improve not only the study of the Whirlpool, but also the calibration of distances throughout the nearby universe. The reliable determination of the Whirlpool Galaxy's distance illustrates the progress of astronomical techniques over the past century. From uncertain estimates based on apparent size and brightness, astronomers have advanced to precise measurements using multiple independent methods. The convergence of Cepheid supernova planetary nebulae surface brightness fluctuations and the Tully-Fisher relation builds a robust picture. Messier 51 is firmly placed at around 23 million light-years, making it one of the best-studied external galaxies in terms of distance. This secure foundation allows the detailed study of its structure star formation and interaction with its companion, all grounded in accurate scale. Computer simulations are essential for reconstructing the history of the Whirlpool Galaxy and its smaller companion. The present appearance of Messier 51 with its symmetric spiral arms, tidal bridge and disturbed companion suggests a close gravitational interaction. To test this, astronomers build numerical models that include stars, gas, and dark matter, governed by the laws of gravity and hydrodynamics. By adjusting initial conditions such as the masses of the two galaxies, their relative velocities and orbital inclination simulations attempt to reproduce the observed structures. Success in matching the appearance of the whirlpool at the current epoch provides evidence for the timing and geometry of the encounter. Early simulations treated galaxies as simple systems of stars responding to gravity. These models showed that when a smaller galaxy passes near a larger disk, it can trigger spiral patterns, tidal tails, and bridges. The Whirlpool system became one of the classic test cases for this approach, demonstrating how a companion could induce the grand design spiral arms. Over time, simulations have become more sophisticated, including not only stars but also gas dynamic star formation feedback from supernovae and the effects of dark matter halos. These improvements allow models to match more subtle features of Messier 51, such as the distribution of molecular gas and the locations of star-forming regions. One of the central questions addressed by simulations is the orbital history of the companion galaxy, NGC 5195. Models suggest that the companion has passed close to or even through the disk of the whirlpool in the last few 100 million years. This passage would have generated strong tidal forces producing the symmetric arms and the bridge of stars and gas. The precise path depends on the assumed inclination and velocity of the companion. Some simulations favor a nearly head-on passage through the disk, while others reproduce the features with a close but off-center encounter. In either case, the interaction is relatively recent in cosmic terms, shaping the present structure of the system. Simulations also test how long the current appearance can be maintained. Spiral arms induced by an interaction can persist for hundreds of millions of years, but eventually they may wind up or fade if not reinforced. The continued symmetry of the whirlpool's arms suggests either that the encounter was recent, or that repeated passes of the companion sustain the pattern. Models indicate that the companion may be on a bound orbit that will bring it back toward the whirlpool in the future. Each passage will renew the spiral structure while also stripping gas and stars from both galaxies. Over time, this process may lead to a full merger, though not for billions of years. The role of gas is critical in simulations. Unlike stars, gas clouds collide and compress when disturbed, leading to bursts of star formation. Simulations that include hydrodynamics reproduce the bright chains of H2 regions seen along the whirlpool's arms and bridge. These models show how gas flows are redirected by tidal forces funneled into arms and compressed into clouds. Star formation recipes built into the simulations then produce clusters of young stars matching the observations. The comparison of simulated star formation patterns with real images is a key test of the model's accuracy. In Messier 51, the match is strong, supporting the idea that the interaction is responsible for the elevated star formation rate. Dark matter halos also influence the outcome of simulations. The extended halo of the whirlpool stabilizes its disk against complete disruption. Without a halo, the passage of the companion would produce more chaotic distortions than are observed. The halo also alters the orbital path of the companion, slowing it through dynamical friction and making repeated encounters more likely. Including dark matter in simulations therefore not only matches the rotation curve, but also reproduces the tidal structures. The need for a halo in these models adds to the evidence for dark matter as a real component of galaxies. Uncertainties remain in the exact parameters of the encounter. The inclination of the companion's orbit relative to the plane of the whirlpool is not directly observed, and different assumptions lead to different tidal features. The mass of the companion is also not precisely known, since its faintness makes it difficult to measure accurately. These uncertainties mean that multiple models can reproduce the general appearance of the system, but details differ. Astronomers therefore compare not only the overall spiral arms, but also fine features such as the thickness of the bridge, the brightness of star-forming regions, and the extent of gas tails to narrow down the best models. Recent advances in computational power allow simulations with millions of particles capturing details on scales from the entire galaxy down to individual star-forming regions. High-resolution models of Messier 51 show gas filaments forming along spiral shocks, magnetic fields threading through the arms, and feedback from supernovae driving turbulence. These models can be compared directly with multi-wavelength observations from optical H2 regions to radiomaps of molecular gas. The ability to match observations across wavelengths provides a stringent test of the physical processes included in the simulations. For the whirlpool, these comparisons support the conclusion that its current state is the result of a recent tidal encounter. Simulations also explore the future of the system. If the companion is bound, it will continue to orbit the whirlpool, losing energy through dynamical friction and eventually merging. This process may take 1 to 2 billion years, during which time the whirlpool will undergo further bursts of star formation triggered by each passage. The final merger would transform the grand design spiral into a more irregular or elliptical system. While this outcome lies far in the future, simulations provide a glimpse of how interactions drive the long-term evolution of galaxies. The whirlpool thus offers a snapshot of a stage in this sequence caught in the midst of its interaction. The use of simulations to study the whirlpool demonstrates the power of combining observation and theory. Observations provide the current structure in detail, while simulations attempt to reproduce it from physical principles. The agreement between the two builds confidence in our understanding of galactic dynamics. At the same time, discrepancies highlight areas where models need improvement, such as the treatment of gas-cooling star formation and feedback. Messier 51 continues to serve as a benchmark for these efforts, its clear structure and accessible distance, making it an ideal laboratory for testing ideas about how galaxies interact and evolve. Despite decades of study, important questions about the Whirlpool Galaxy remain unresolved. The timing of the interaction with its companion NGC 5195 is still debated. Some simulations suggest a nearly direct passage through the disk a few 100 million years ago, while others favour a more tangential encounter that nevertheless produce strong tidal effects. The lack of consensus arises because different models can reproduce the broad spiral structure but diverge in the details of tidal tails and velocity fields. Until more precise measurements of the companion's mass, orbit, and motion are available, the exact history of the interaction will remain uncertain. Another open issue concerns the longevity of the spiral arms. Density wave theory explains how arms can persist for long periods, but whether the whirlpool's pattern is maintained by internal processes or continually refreshed by encounters is not fully established. The symmetry of the arms and their sharp definition suggest tidal reinforcement, Yet the presence of organized dust lanes and star-forming sequences aligns with predictions of steady density waves. Determining the relative contributions of these mechanisms requires both more detailed simulations and long-term monitoring of star formation patterns across the disk. The role of magnetic fields in regulating gas flows also presents uncertainties. Observations show that fields align with the spiral arms and are compressed by density waves, but how much they influence star formation efficiency is still debated. Some models indicate that magnetic pressure delays collapse of molecular clouds, while others suggest that fields channel gas into filaments that promote collapse. In Messier 51, the correspondence between polarized radio emission and star-forming regions is strong, yet disentangling cause from effect remains difficult. Future observations at higher resolution may clarify how fields interact with turbulence feedback and gravity in shaping the interstellar medium. The nature of the central black hole and its activity level is another area of study. The nucleus of Messier 51 shows signs of being a low-luminosity active galactic nucleus with weak X-ray emission and spectral lines consistent with ionization by accretion processes. However, the exact accretion rate and variability remain uncertain. Some studies classify the nucleus as a low ionization nuclear emission line region, while others favor a safer Type II classification. Distinguishing between these categories requires precise measurements of emission line ratios, X-ray variability, and infrared signatures of hot dust. The low brightness of the nucleus makes it challenging to separate nuclear activity from surrounding star formation, leaving its true nature ambiguous. The efficiency of star formation in the whirlpool raises questions about the broader regulation of galactic evolution. Observations show that star formation rates are elevated compared to isolated spirals consistent with tidal triggering. Yet the overall conversion of gas into stars still follows scaling relations known as the Kennicutt-Schmidt law, which links gas surface density to star formation rate. This suggests that even in an interacting system, fundamental laws of star formation apply. Understanding why interactions enhance star formation without breaking these scaling relations is an active area of research. Messier 51 serves as a case study, but broader surveys of interacting galaxies are needed to generalize the conclusions. Uncertainties also remain about the composition and distribution of dark matter in the whirlpool. Rotation curves clearly show the need for an extended halo, but the exact density profile is not uniquely determined. Different models of dark matter predict slightly different shapes for the halo, and the whirlpool's data do not yet distinguish between them. Additionally, the influence of the companion complicates interpretation, since tidal interactions perturb the velocity field. More precise mapping of velocities at large radii may help refine the dark matter profile, but for now the details remain elusive. The presence of dark matter is secure, but its exact distribution is not. The metallicity gradient in Messier 51 also invites further study. Observations show that heavy element abundances decrease with distance from the center, reflecting the history of star formation and enrichment. However, the interaction with the companion may have stirred the gas, flattening the gradient compared to isolated galaxies. Determining how much mixing has occurred, and whether inflows of gas from the outer disk or from the companion have altered abundances is an open question. Such mixing processes are important for understanding chemical evolution in galaxies, as they influence the availability of enriched gas for new stars and planets. The ultimate fate of the whirlpool system is another subject of speculation. If the companion is bound, repeated encounters will eventually lead to a merger. The timescale for this process depends on the mass of the companion, the density of the dark halo, and the efficiency of dynamical friction. Some models suggest a merger within 1 to 2 billion years, while others allow for a longer timescale. The merger would transform the whirlpool from a grand design spiral into a more irregular or elliptical system. Observations of other interacting pairs provide analogues, but predicting the exact trajectory of Messier 51 remains uncertain. Open questions also extend to the star clusters formed in the interaction. Thousands of young clusters have been catalogued in the whirlpool, but their long-term survival is unclear. Many clusters dissolve within a few 100 million years due to internal dynamics and external tidal forces. Determining which clusters will survive to become globular clusters and how interactions influence their survival rate is an active area of research. The distribution ages and masses of clusters in Messier 51 provide clues, but the answers are not yet complete. Future observations with new instruments may address many of these uncertainties. The James Webb Space Telescope will probe the infrared emission from embedded star-forming regions and measure the tip of the red giant branch for improved distance estimates. The Atacama Large Millimeter Array will map molecular gas at high resolution, tracing the flows driven by density waves and tidal forces. Next-generation radio telescopes will measure magnetic fields and cosmic ray propagation in greater detail. High-energy observatories will refine measurements of the nucleus and its variability. Together, these tools will deepen the understanding of the whirlpool while highlighting new questions. The Whirlpool Galaxy thus remains both a familiar object and a source of continuing mystery. Its arms, dust lanes, star-forming regions, magnetic fields, nucleus and companion have been studied across the spectrum, yet the system still holds uncertainties about its past encounters, present processes and future evolution. The combination of clarity and complexity makes Messier 51 an enduring focus of research. It is close enough to be studied in detail, yet distant enough to represent an external system whose properties can be compared to many others. For astronomers, it is both a model and a puzzle, inviting observation, simulation and interpretation without offering every answer.